So in the previous video we have seen that the form of the x momentum equation is this, and then now this was derived by using the proper dimensionless variables. Let us try to now see what happens to the y momentum equation. The y momentum equation for a steady state may be written as following. So now let us write down the equation in terms of the non-dimensional variables. So the first term is rho u del v del x, which is nothing but rho u infinity v reference by L times u bar del v bar del x bar. But we have already seen in the previous from the continuity equation that v reference by delta scales with u infinity by L, and thus this magnitude may be written as rho u infinity. So basically Vr equal to u infinity times epsilon, so u infinity square epsilon by L. This is the first term. Second term may be similarly obtained, rho v reference square by delta, but v reference, so v reference, let's write it down. Sorry, this should not be bar. So this is equal to rho into v reference, so let us multiply and divide by delta. So v reference square by delta square into delta times v bar del y bar, and this is nothing but rho, but Vr by delta is the same as u infinity by L, so this becomes u infinity by L whole square, because this is Vr by delta whole square, and Vr by delta is nothing but u infinity by L times delta times v bar del y bar, and this is nothing but rho u infinity square by L times epsilon, because we can take one of the L from the L square and combine it with delta to write as epsilon. So both the terms on the left hand side have the same order of magnitude, which is basically rho u infinity square by L times epsilon u bar by del x bar plus v bar del v bar, so this should be v del y bar. So del p del y is equal to minus rho u infinity square by delta times del p bar by del y bar, and the next term will be mu into u reference, which is u infinity times epsilon by L square. If I take everything common, del 2 v bar by del x bar 2 plus 1 by epsilon square del 2 v bar by del y bar 2. I'll let you do this as a small exercise. It's really easy to show. There's nothing complicated about this. Okay, I simply take mu v reference by L square outside, but v reference is nothing but u infinity times epsilon. So it's a very simple thing. I've skipped only one step. And so let us simplify this as following. And so minus rho u infinity square by delta may be written as minus rho u infinity square by epsilon, so by L into 1 by epsilon del p bar by del y bar, because by definition delta is equal to epsilon times L. And then lastly we have u infinity by L square epsilon del 2 v bar by del x bar 2 plus 1 by epsilon square del 2 v bar by del y bar 2. And then we simply divide everything by rho u infinity square L. So on the left hand side we have epsilon u bar del u bar by del x bar plus v bar del v, this should be v, my bad. So this is v bar. Okay, we are writing the y momentum equation is equal to minus 1 by epsilon del p bar by del y bar plus epsilon by re del 2 v bar by del x bar 2 plus 1 by epsilon square del 2 v bar by del y bar 2. But epsilon we have already seen is equal to 1 by epsilon square. Reynolds number we have already seen is 1 by epsilon square. And thus that allows us to write the following. Epsilon cube del 2 v bar by del x bar 2 plus epsilon, because epsilon cubed and epsilon square will give us one epsilon over here. And thus consequently in the limit epsilon tends to 0, this is the term that will be most dominant. All the other terms will be asymptotically 0. So at leading order, the boundary layer equation for the y momentum equation yields del p del y is equal to 0. The implication of this is p does not vary with y. It does vary in y but asymptotically. The leading order, it does not vary in y, and thus the pressure is said to be imposed on the boundary layer. So whatever is the pressure in the free stream, so this region is called as the free stream. Whatever is the pressure in the free stream, because you can find out that pressure using the Bernoulli equation, that pressure at this point will be the same everywhere. The pressure is not varying in the y direction. Okay. So if this is the boundary layer and if this is one of the streamlines, that is, these are the inviscid streamlines, the pressure here is said to be imposed on the boundary layer. So the pressure at this point in the boundary layer is same as this. And the pressure outside, which is inviscid, is obtained using the Euler equation or the Bernoulli equation, which are practically the same thing. The pressure inside the boundary layer varies along x only for a steady flow. If the flow is unsteady, then it will also vary along in time. So inside the boundary layer, the pressure is imposed. That's a very important conclusion of the y momentum equation. So in the next lecture, we will look into the momentum integral theorem of von Karman. Okay, see you.